All right, thank you. So yeah, we're going to talk a little bit about recent additions. I mean, when we say recent, some of this is really recent, some of it's really work that was kind of finished up last year, but taking the time to maybe talk about it a little bit more this year. So it's faster, it's unsteady, it's noisier, and all the old bugs have been replaced with new ones. That's it in a nutshell. So it's faster. So between pretty much the release from last year and the release that's out there now, I'm going to have one up there soon, I think, because we found some bugs that I've been working on, is the agglomeration multipole has been updated. So I talked about that in the theory, what that was. It's faster now. Part of that is that that process runs in parallel, so all the agglomeration and setting things up, that's done in parallel. So if you're running in parallel, that part of the solver will run faster. We've improved the agglomeration process itself, so it generates some better coarse grids, more aspect ratio constrained grids, and a little bit more accurate transitions between the final coarse grid approximations. And then the biggest one, backward propagation of the agglomeration. So I already talked about, if you sat through the previous talk I had about, this whole thing about far away and using approximations to calculate the induced velocity at point P, by a group of vortex panels. That sped things up. So you don't necessarily have to do n evaluations of every panel evaluated for every other panel. So it was like n squared. It was more like n log n. So now the agglomeration has been implemented to speed up that evaluation in the other direction. So now if you have a bunch of points, P1 through P sub n, and if those points are all close together and they're also all far away from a group of panels, you can now basically speed that process up twofold. So back to, we discussed that we had, a point P and a group of vortex loops. We could speed that up by basically agglomerating those into a single loop, assuming P was far enough away. But now, what if we have a whole bunch of points, P1 through P6, and we have that same group of vortex loops, 1 through 6? Well, if those points are all close together, and if they're all far away from those vortex loops, we can basically replace all those points with a single point. And we can basically do that distribution calculation to that single point and then basically distribute it to the other points. So in general, by doing that, we're seeing about a speed up of 2. There's a whole bunch of other things that have gone into the code to improve accuracy, but in general, that one little piece of update basically for a lot of models that I run, like in the panel mode, but even the Vortex Lattice mode, generally speed up on the order of 2. So the SkyMaster one takes about 30 seconds on my laptop, takes about 17 seconds now, version 6. At F15 active geometry was about 50 seconds. It's now about half that. Somehow that got out of the way. All right, so it's unsteady. Current version supports unsteady analyses, so we can do things like dynamic stability derivative estimates, time-accurate modeling of propellers, and some first steps towards full 6-DOF that I'll show just some pretty pictures of at the end. So unsteady analyses. So the biggest thing here is that you've got pretty much 2 things that are going on. You've got time-dependent boundary conditions. So we have that basically tendency boundary condition that we had before, but now those rotors are moving, bodies are moving, wakes are obviously moving because they're unsteady now. And so that boundary condition is now not just fixed geometry. You have to take into account that there is moving geometries like rotating propellers. You have to do time-accurate convection of the vorticity in the wake. So at a simple linearized level, the vorticity gamma is convected downstream in the wake. So you don't have these wakes that go off to infinity, and you're not just solving for a steady state weight, shape, and distribution. Instead, as you step through time, you think of time zero with a wing in a tunnel, and you turn on the tunnel. The wake starts to shed as the time goes by. That wake starts to move downstream, and initially the wing is generating no lift. At some point, it's generating some lift, and then that lift, as time goes off, hits some steady state value. And so the wakes have to be convected in a time accurate way, and the vorticity on those wakes isn't constant from the trailing edge all the way off to infinity. It's varying as a function of time, and so it's varying at downstream stations. And then finally, there's unsteady terms that show up in the evaluation of both forces and moments. So there's a delta P unsteady term, which is basically proportional to d gamma dt that shows up in the Bernoulli equation. So like I said, you have time stepping wake. So now if you want to evaluate the induced velocity at some point P, and you've got some lifting lines, as you step out, time equals delta T, you shed a bound vortex, you do 2 delta T, now you shed another bound vortex, and the previous one is convected downstream. You go to 3 delta T, you've got 3 shed vortices. Each one of these are, basically U delta T, where U is some, free stream velocity downstream, right? And I right here, they're all basically convecting at the same speed. In reality, the wakes and all the geometry is all interacting with the free stream. So the velocity that each one of these bound vortices moves downstream is, affected by all the other things that are going on in the flow fields. And they're not going to be just convecting as, straight marching in some uniform velocity. So this has all been implemented in the code in terms of doing unsteady time accurate analyses. One of the first test cases that we did was just a 2D oscillating airfoil. So this was modeled with a high aspect ratio wing. We turned off basically the trailing vortices, if you want to call them. Only the bound vortices are modeled. So we basically turn off the tip vortices that would show up in a finite wing geometry model. So this is a high aspect ratio wing. It's really essentially acting as an infinite aspect ratio wing, just to see how well we're calculating the bound vortices that need to be modeled in general for 2D or 3D. And the nice thing is that in terms of a 2D oscillating airfoil, there's an exact solution by Theodorson. So let's see if this actually will play. So I don't know how well this video is showing up, but basically you've got a pitching wing, or essentially a pitching 2D airfoil, and as it's pitching, it's shedding those trailing wakes, and you saw it initially, it had a start up there. We can start this up again. And so they're shed off, and then at some point it basically hits a steady state, and this thing is just basically running, pitching, and you can see, the shape of the trailing wake is obviously affected by the oscillating motion of the airfoil. Now, if this was a finite wing, if we were actually modeling all the tip vortices, and the thing would start rolling up, and you'd get obviously much more complex wake geometry in the far field. But here we're just trying to capture essentially a 2D type solution, so we can compare against a exact 2D solution by Theodorson. So if we plot up both angle of attack and lift coefficient as a function of time, we can see what's going on here. And so there's a phase shift. So the angle of attack is going, plus or minus 5 degrees, and the CL is pitching up there in the greenish blue line, plus or minus about 2.5. And once we get out here, like 60 seconds, it starts to hit a steady state solution. Really, there's some initial startup going on there at say 0 to 30 seconds, and there's a phase shift between the peak of the angle of attack occurring and where the peak in lift coefficient occurs, and you can predict that from theory. Theory says about 210 degrees. VSPAERO would get to about 198 degrees, and this is with a time step of 1 second. Next case was the standard dynamics model. So this is a fighter-like geometry, kind of F-16-ish. It's been used in both wind tunnels and ballistic range models to basically predict things like CM alpha dot, CM plus CMQ, CM beta dot, etc. So those damping derivatives. So there's experimental data from both wind tunnels and the ballistic range shots. The right is my oversimplified model of that vehicle in OpenVSP. And then if this will run. So this is just a repeat loop. Basically, it's doing a pitch up, pitch down. It's doing one full cycle of that to capture basically the unsteady behavior. Look at things, lift, drag, and moment as a function of time and obviously angle of attack. So using that data from this short analyses, we can basically back out things like CM alpha dot plus CMQ. And I did that across the Mach number range. And so on this plot is CMQ plus CM alpha dot. When you do that unsteady analysis, you can't really differentiate between, are you calculating CMQ or are you calculating CM alpha dot? They really show up in the same kind of behavior. So it's the net of the two that you can actually calculate. And the same goes when you do the ballistic tests or the wind tunnel. It's the net of those two things that you're actually able to measure. So there's wind tunnel data on here. There's range data on here. There's CART3D, which is an Inviscid Euler solver, results on here by Scott Merman. And then in purple or cyanish is the VSPAERO results. And this is running the vortex lattice model, so I ran it all the way out to Mach 1.2. And in general, for where there's data at 0.6 up to 1.2, we're doing, I would say a reasonable job. We're not capturing. There's obviously some kind of spike going on. CART3D sees it, in the Mach 0.9 range and that transonic range. We are a linear model with linear compressibility. So I'd say the fact that we're, in that basically ballpark range of being able to predict CMQ for CM alpha dot is kind of amazing. Next one is the isolated rotor. So this is basically a test case that was provided by Uber. Rob gave this to me. Thank you for that. We ran it in the vortex lattice mode. All the inputs there, standard single day, inflow of 10 feet per second, about 186 RPM, tip Mach 0.4. And this was run out in a time accurate analysis for 10 revolutions. And then the geometry there is shown in the lower right, and the details of the geometry in the table up there in the upper right. So this is, let's see if this plays. So this is just starting from, an impulse start, the rotor sitting still, then boom, it's going, inflow turns on, and so you get a very startup-ish looking wake there that gets blown downstream. Again, this is running for 10 revolutions, and then it's going to restart the video. And we chose 10 mostly because that's what Rob chose for the other solvers that they were using to evaluate this rotor, basically as a benchmark test case. We'll let this run one more time. Hopefully this video is coming across somewhat. So screen captures on this. For some reason, the captions didn't show up. So the right is, I believe, overflow, and the left is VSPAERO. So just comparison of the high fidelity CFD against what VSPAERO is getting in terms of the wake geometry on this vehicle, or this isolated rotor, sorry. And then just looking at the load on one of the blades. So we've got two sets of data here. In green is the overflow, and the box, yellow box with the line is VSPAERO. So this is basically force pounds per foot from the root out to the tip. And you can see the effect of that showing vortex from the previous blades affecting the solution out there near the tip. But in general, VSPAERO is doing a really good job of not just qualitatively kind of predicting that shape of that downstream weight, but also its effect on the overall loading of the rotor blade. And then in terms of power, so this is basically horsepower per foot along the blade from root to tip. And again, we're seeing some very reasonable comparisons between overflow and VSPAERO. Next is the not so isolated rotor case. So this is Uber Elevate's Concept 2 vehicle. Bunch of rotors, both cruise and lift rotors. So we've been using this internally just as like a benchmark case to put together some test models. So this is running a standard zero a day. We did a basically 150-foot flyby at 68 miles an hour, running this in the Unsteady vortex lattice model. And again, it's running 10 revolutions on the slowest rotor. All these rotors aren't running at exactly the same speed. Let's see if this runs. We'll let this run out. So you've got the cruise rotors, you've got the lift rotors, you've got the wakes coming off all the wings as well, and tails. So this, again, is running out 10 revolutions of the slowest rotor, which I believe is one of the rear lift rotors. We'll let this run out one more time. Okay. Kind of blowing through all this. So it's noisier. We talked about this before last year. So this integration is in there fully. We support outputs to PSC WAP. So if you want to do noise prediction, you can do it using the vortex lattice model process now. It uses that to get the loading on all of the components, so bodies, wings, tails, as well as rotors. That's all written out in the format that PSC WAP would expect. It also writes out the full geometry, so you get the thickness effects, the full fuselage is there, the full wing is there in terms of the volumetric effects when you're calculating both the monopoles and dipoles for the noise. You can do unsteady, periodic, or aperiodic analyses in terms of what, with PSC WAP. And so, like I was saying, VSPAERO automatically kind of creates the thickness geometry files, the loading files that PSC WAP requires. And then it, along with all that information, I also write out basically the nameless driving files. So you get one file that basically has the entire vehicle plus all the rotors in it. So if you run that, you basically predict the noise for the full up vehicle and whatever flight configuration you're doing this analysis. I also write out a file that basically just drives PSC WAP with just the vehicle, no rotors, so you can discriminate out what noise is coming from wings and tails and things like that. And then one file, and it really should say for the vehicle plus rotors. So you basically can run up the full up vehicle and then run that full vehicle with each individual rotor. And so you can kind of isolate, the individual noise from each rotor and back out basically which one is perhaps contributing more than others. And then finally, you can run VSPAERO at whatever optimum time step is appropriate for getting the aerodynamic unsteady analysis correct. You run VSPAERO, it generates that unsteady analysis, all that's saved out to a file. And then there's a post-processing step that you do with VSPAERO that'll create the POC walk-off input files. And it will basically do an interpolation through that unsteady analysis data that it's saved out to disk, and do a cubic interpolation in time to generate the loading and geometry information, because obviously things like rotors are moving as a function of time. So it will output the unsteady geometry and the loading at a delta t that's appropriate for POC walk-off. And so those two delta t's don't need to be the same. I don't know if this is going to play, but I don't know if that's coming across at all, but basically,
it's coming across well, Dave.
Yeah, and this is playing on my laptop speaker, so it's not quite right. But the point is that out of that entire analysis, again, we did a flyby. It's observer sitting there, the vehicle's flying by at 150 feet overhead. Comes in, flies over, and continues flying down range. And PUC WAP predicts what that sounds like. And presumably, if I had the right sound equipment with the right speakers, this would sound a little bit better than it sounds on my laptop. Yeah, I don't know if I have that on Linux. I don't know that I've looked. I don't think it's there. So final test case. So in case you want to drop a bomb from a CRJ, you can. So we're working on basically being able to do full 6-stop multi-body analyses with the solver. And so it's actually not that big a deal. All of the underlying framework is there. We're already doing, rotating geometry for the props. The way the code's set up, it doesn't really matter if it's rotating, translating, or a combination of the two. So I basically took the CRJ model that I had and used the pod geometry and threw some fins on, and you have that. So to do a multi-body 6-off analysis, you can run it in either the panel or the Vortex Lattice model. Right now, it's only doing viscid forces and moments, so it's not bookkeeping basically the viscous forces. There are some methods in there for the Vortex Lattice for calculating those, but I'm not using them. For the panel method, it's purely inviscid. Requires you to input, obviously, mass and inertias for the unsteady components, so for those things that are moving. And in this case, you'll see, just to make it a little bit interesting, I basically moved the pod off axis just to make the starting condition a little bit more fun. And then I would just say this is a work in progress. So there'll be an update with this stuff in it, quote unquote, soon, so people can play with it. It's just mostly they're going to have to run it at the command line because none of this stuff is supported really at the GUI level, I don't think. So that's the panel geometry with the initial condition for the pod. If we run this, so it's doing the unsteady analysis. It's drilling the wakes of all the lifting surfaces for both the wings on the airplane as well as the fins on the pod. And at each time step, it's integrating the forces and moments on all the vehicles, but then it's obviously only using it for the pod to calculate where it's going to be at the next time step. So this runs actually fairly quickly. I mean, this is, like a 20-minute analysis on my laptop. So I think that's all I have. Questions?
We've been getting quite a few questions online. I'll encourage people to keep asking them. I'll try and forward some of those to you, Dave, that we haven't already answered. Let me see here. Can you tell us a little bit more about the 6-DOF? Is that, I know it's not supported in the GUI. Is that in the release version of the solver, or is that still a work in progress?
So the version that's out there now, you could run it now, but it would be wrong. So it's a work in progress. So if somebody were to grab the solver that you put up there now, you could actually run some of these cases, but the 6-DOF solver is, let's just say, broken. I mean, it'll run, but it's not quite right. And so basically what's not in there is it needs to basically translate forces and moments from body fixed, to the neutral or vice versa. And so that part of the code wasn't finished when I gave the last version to you. So that's what's in my version now. So once I get an update to you, this will be there. So all the 6-DOF, it's all done in quaternions in terms of integrating the forces and moments. And so there's a step in there where you basically have to, translate forces and moments from inertial to the body and then back, to get the rotations back. And so that's in my version. It's not in yours.
Okay, great. One question.
In terms of the GUI, in terms of the GUI, I mean, some of it was kind of there. I'd have to go through and see. I don't know what they may have put in the GUI because some of it was kind of in there. So if somebody was like bored, they could have added some of the inertia stuff. Because if you looked in there, some of the values that are in the group files include things like mass, inertia, initial conditions, and those are the things I'm using. So none of that's changed. But my guess is that you're going to have to edit those files by hand at this point and run this from the command line.
Yeah, that's correct. Right now, the GUI will set up a rotating blade case, and it'll help you with the stability cases that do the roll pitch yaw pulses, but it doesn't set up the 6-DOF case.
Yeah. So I mean, all that input stuff is there, but I mean, it should be fairly straightforward. Speaking with the person who doesn't have to do it, to add that.
Okay, we've had a question here. I don't entirely understand the question, but somebody asked for you to talk about the shedding spanwise vorticity. So are you capturing the shed of spanwise vorticity or not? The question says there's a lack of spanwise vorticity. So if you have any thoughts in that.
I'm not sure I understand the question.
I'm not sure that I do either. Maybe they can restate it a little more verbosely. So I'll come back to that.
I mean, if they're talking about the unsteady 2D case, that was specifically forced to be 2D. So, in terms of spanwise variation, it was turned off. Right? So if you think about Stirling wakes for the unsteady case, there are the trailing wakes that you have in the steady case, and then there are bound vortices that you have to shed as well. So the code models both. It modeled, the trailing vortices originally. It always did that, although they were assumed to have the same vortex strength from the trailing edge off to infinity. Every, it varies as a span in the spanwise direction, obviously, because your loading's varying. But the value for a given trailing vortex is the circulation strength for that given trailing vortex in a steady state case. It's constant from the trailing edge off to infinity. In the unsteady case, that's not true. Over each time step, you that trolling weight moves downstream some distance, u times delta t, and use a local velocity, and then you shed a bound vortice, and so you basically have a standwise distribution of vorticity, but then you have a distribution, from the trailing edge all the way out to infinity distribution of vorticity as well, because those bound vortices initially are changing as a function of time. If you hit some steady state, then they're constant as a function of time, but you still have that distribution going out in the unsteady solver. So on the unsteady case I showed with comparison against Theodorson, numerically went in and basically forced the solver to act as if it were 2D. So it turned off the spanwise variation of the trailing vorticity, and we only modeled the bound vortices that are a function of time and obviously distance that is the downstream. And that was so that we could compare it with an actual CD solution.
Great. Dave, is there, in addition to the 6-DOF, is there support for prescribed motion? And then if there is, while it wouldn't necessarily be there right now, would there be a path towards prescribed motion with an articulation? So, for example, tilting a wing or deflecting a control surface in the time of the solution?
Yeah, so you can do that now. So, I mean, the hooks are in the code to do that. Essentially, the 6-DOF is using those hooks. So yeah, you can go in and specify components, dynamic components, and basically force them just to have some specified motion. But right now, that motion is very simple. It's basically, X, Y, Z velocity, and obviously propellers, which are basically, rotation about a fixed axis. So all the hooks are in there for that. Yes, we have to figure out how we wanted essentially to be able to set that up, right? Because the setup for that's going to be the harder part. I mean, so if you wanted to have a flat deploying, or if you wanted to do like a V22, right, a lot of it's going to be nested levels of roots, so that you could have a rotor that's tied to a nacelle, and then have a nacelle that's rotating about some point fixed to the wing. So it's a lot of bookkeeping, but all of the mechanics to do that are there in the code. And it's open source.
Thanks, Dave. I agree. The setup of the problems, and they're very general problems, so everybody's going to have a different problem. So capturing that generality in the GUI is very challenging. There have been a lot of questions about is there a validation publication and or a theory document or documentation of all the options for the files in the command line. I know I pester you about this all the time, so I figured I'd embarrass you in public. Do you have any comments about that?
Like, good luck embarrassing you, but yeah. So I'm actually working on a document. You'll be happy to know, but I'm not going to say when it'll be done. But I actually have started putting together all these different test cases and writing up a theory document. I mean, as far as the stuff that's on the command line, I mean, I think some of that's like sort of documented somewhere, isn't it? In terms of running it on the command line. But I mean, I could certainly put together that quicker and sooner than later.
Yeah, the command line options are documented, but things like if somebody wanted to do a 6-DOF file and they'd have to figure out what went and how to set up the groups and how to set up all those files themselves. So that's not. I don't think there's documentation right now.
Well, I mean, that's a good point. So I mean, I think once I come up with a version to release to put up on the website, I mean, I can put together a simple 6-DOF case and some documentation to go with that. to show how it's done.
Great.
Dave, I wonder, can you mix actuator discs and group prescribed motion in an unsteady case, or will that not work?
I've never tried it. In theory it should work, but I've never actually tried it. Trying to think of what would break. I don't know. Something probably would break, but because I honestly haven't tried doing that.
Okay. It might be something that I try and see if I break something.
Yeah, we have a little bit of time. Right now you have the actuator disc model, which obviously runs steady state very fast. It really doesn't slow anything down. And if you're doing propellers, it's a good place to start. And then we have the full Unsteady, which is great if you're doing things like that over two geometry, or something, that is just, you can't capture the actuator disc model. I am working on something in between. So I've got a couple different things in terms of like essentially a blade helmet type model that hopefully, I'm hoping we'll have something in between basically having the time step and wakes, but not having to do an unsteady analysis. And then something that basically will, would work in terms of edgewise flow for something like, an Uber vehicle with basically rotorcraft type flow. But give you a steady state answer. And so you don't have to run unsteady code. So maybe this time next year we'll have something like that.
Hey Dave, this is Justin. I have a quick question. A little while ago, you mentioned to me that you were working on being able to basically run some components as panel method and others as VLM. Is that something that you're still working on?
Yes, I am. And a lot of it's going to be driven. So I have a hack together piece of code that'll do that because the solver really doesn't care. The solver, it's the exact same solver for both the vortex lattice code, models and the panel. It literally is the exact same solver. There's one additional constraint that I didn't talk about that goes into the panel code. Basically Kelvin's theorem constraint, but so there's that. But other than that, 99.99% of the solver is identical. So it really could care less. It's just right now we kind of have like two paths for setting up the geometry. So so I've hacked together models that basically have VLM components in there on the panel components, and so you could run a mixture of the two. I actually think that would be quite useful for some things. It would require us on the GUI side to be able to mix and match things.
Hey, Dave,
No, that's an exciting option. We should also theoretically be able to do a modification to CompGeom that would allow you to trim potato chip surfaces by thick bodies, and that would let you get interesting, thin surface wings with fat fuselages while doing a reasonable trimming, which would be cool.
Yeah, and that's exactly like kind of the models I think would be useful for some cases.
Dave, this is Brandon. I mentioned in the demonstration earlier that the parasite drag component of the output file, namely in the polar and the history files, not only includes that NACA 12 formulation of the parasite drag, but you've also added a viscous curve fit, I believe you mentioned. Could you elaborate a little bit on that?
Sure. Yeah. So for the vortex lattice model, for wings, it will go in and basically uses a NACA 0012 curve fit for the skin friction, at zero angle attack, and then a curve fit of CD as a function of 2D lift coefficient. So if you're running the vortex lattice model, the nice thing about that model is that the way the wing comes in, it's essentially a structured mesh. And so you have all those spanwise airfoils that you've defined or are interpolated from the ones that you have defined. And so the code can go in and integrate, at each one of those span stations to get, the 2D lift coefficient. And then it can use that 2D lift coefficient to go into that curve fit for the NACA 0012 to come back with what the zero lift drag is at that 2D lift coefficient. So, like you said, it comes up with an estimate for basically the zero lift drag, and then it's got basically a quadratic curve fit, to that NACA 0012 data, and then it's got kind of a correction in there for Reynolds number. What Rob and I agreed is the way to go is ultimately to replace all that with tabular data. So you can have all the NACA. I mean, there's tons of that data is available on the web. So if we had access or a format, basically a consistent format, then we can basically interpolate that 2D data to get the 2D zero lift drag on the spanwise direction of these vortex lattice models. For the panel models, that doesn't work right now because I don't have an easy way to integrate and get that basically spanwise 2D distribution. But that's something that I think Rob and I think we have a solution to how to do that. I just have to get around to doing it. It's on the list.